differentiation of bases other than E. So not natural base E. You guys probably don't remember because it has been a little while. But this was the section we were working in, and we didn't get very far. Essentially, what we did was we discussed a little bit about how we could define functions that were not base E, so general base, like a to the x here. And one of the simplest ways was to redefine it using e to the ln of a times x. And then e to the ln of a is the same as a. And so then we've got what's left, if you throw an x on there, is a to the x. There's a nice little neat trick that allows us to redefine a function so that it is base e. Why was that important? Because later down the road, we used that definition to find the derivative. Oops, I forgot I did these as separate slides. You'll have to bear with me. I'm working on a new software here. This is not Notability, which is what I had used for everything in class so far. Instead, this is Explain Everything because it records easier and differentiates me to post those recordings. Okay, here we are for our first video lesson. We left off in the last class we had in person, part of the way into section 5.5, which was on basically integration in a more streamlined way. So I'm switching softwares for the purpose of the online course. Excuse me. So here we are. We rewrote it in terms of E so that we could then, right here, so that we could then differentiate. So let me do a quick review of those differentiation rules because I'm not sure we remember them. So up until this point, let me see if I can remember them off the top of my head. I had these written on the side of the board, on the right side of the board where the projector was in the classroom. We have learned that, let's see, first of all, the derivative with respect to x of, let's back up just a hair, of the natural log of u was equal to 1 over u, 1 over the input u times the derivative of the u prime. Or I think the more formal way to write that would be du dx, but I'm going to leave it u prime. We learned then that the integral of 1 over u is equal to the natural log of the absolute value of u plus c. We learned that the derivative of e to the x is, I'm going to go e to the u actually instead of e to the x. The derivative of e to some power of x, and if that power is not just x but some function of x, then it's e to the x, e to the u, and then times du dx times u prime. And then what else did we get to so far? We've talked about the integral of e to the u du would then just be e to the u plus c. Of course, there's a lot going into that. We got to have a u prime somewhere in our integral. But for now, that's about as far as we went. And so here we are. We've transitioned now to where we are talking about taking a derivative of things that are not base E, but are of any base. And the simple rule is the one that is outlined here in this red box. It is the original original exponential function, a to the x, times this extra factor of ln of a. And ln of a is just a constant. And technically, if we were applying this same rule that I just highlighted here in red to our e to the u function here, then if it was just basically e to the x and we were differentiating, then we would take the original exponential, e to the x, which of course mimics what's there, and then we would multiply by the natural log of e, if we were following that same rule. Multiply by ln of e. But ln of e is just 1, so we don't need it there. Again, the derivative of any exponential function is the original exponential function rewritten without any change times natural log of the base times the derivative of the exponent. And that is what is illustrated here in number 2. The derivative of any exponential function is the derivative of the original exponential, is the original exponential, that is the a to the u here, times natural log of the base, that's the ln of a, times the derivative of the exponent, that's the du dx. All right? So if we're applying that rule, we actually did these 2 examples, I believe, in class, but I'm going to do them again. If we're applying that rule in a, then we get a very simple y prime is the original exponential 2 to the x times natural log of the base ln of 2 times the derivative of the exponent, but the derivative of the exponent is 1, so we don't really need it there. So our final answer is just 2 to the x ln of 2. All right, and that was, again, that's rule number 2 up there. This, the same rule can be applied. You could say it's rule number 1, by the way, if you were comparing it. But the fact is, if you just memorize rule number 2, it kind of takes care of rule number 1 also. So I'm all about trying to streamline and use less rules if we can. So that's why I would say memorize rule number 2, and then go on and memorize rule number 3 or rule number 4 here. This is for the derivative of any general log instead of general exponential. But we will get to that in just a moment. For now, let's do b again real quick. For b, if I'm trying to take the derivative of 2 to the 3x, then it is, again, the original exponential, 2 to the 3x, times natural log of the base, that's ln of 2, times the derivative of the exponent, which is another factor of 3. Again, this is the derivative of the 3x, the exponent. So the final answer, you could, if you wanted, you could multiply the ln of 2 times 3, and you're going to get some decimal. That decimal actually turns out to be 2.079. Or you can just leave it. Most would probably just leave it. You could rearrange it. You might find it in a rearranged form somewhere, but usually it's not going to be written any other way than that. All right? So let's go on to the next page. On the next page, we're going to require this number 4, property number 4 that I've highlighted here in the purple. So take a look at it now and maybe rewrite it on the next page. The derivative of the log with any base, not base e, so not ln, but base e, or base a. Compare that to the formula here at the top, the derivative of the natural log. The derivative of the natural log was 1 over the input times the derivative of the input. Well, this is not too different. The derivative of base a is 1 over, look where I'm circling here, 1 over u, 1 over the input, and then we have, again, the derivative of the input attached to it. The only addition is this extra factor of ln of a in the denominator with the u. Let's see why that is. We go on to the next page, which, by the way, is exactly the same as number 4 here. All right? And here is a proof, a very quick proof. If we rewrite the general base a using the change of base property here, which you may or may not remember, I think we highlighted that in the second page of these notes when we were in class. This is the change of base property here. we rewrite it in this way, then that 1 over ln of a is essentially just a constant we can pull out, because that's what ln of a is. A is a constant, and so ln of a is still a constant. And so really what we're looking at is just the derivative of ln of x. And the derivative of ln of x is 1 over x. So if you take that 1 over x and you multiply by the extra factor of 1 over ln of a that was out there, then you end up with this 1 over x ln of a. And so there it is, again, boxed in our red box here. The derivative of any general logarithm is 1 over the input times natural log of the base. And then if I was going to make this even more general, I would say, whoops, hold on. This is the formula you should probably memorize. Hold on 1 second, sorry about that. The formula should probably be, if it's in terms of u, then the derivative with respect to x of any general log base a of u is 1 over u times natural log of the base times u prime. So we multiply by the derivative of the input if the input is something other than x. In this case, if it is x, if we're multiplying by that derivative, we're just multiplying by 1. All right? So let's look at that in example. Example C here has log base 10 of cosine of x. So it's a perfect segue, perfect connection to the red form that I just. So there's our formula. So let's go. Y prime is equal to, since it's a log, it's 1 over the input, 1 over cosine x, times natural log of the base, so that's ln of 10, times the derivative of the input, so it's the derivative of cosine, which gives me technically negative sine on top over cosine times ln of 10, and negative sine over cosine is really negative tangent. So I could say that this is negative tan all over ln of 10 could be my answer. I'm not saying you'd have to go all the way out to that and write it in that way, but that's probably the way that it would be shown. If there was an AP question that was a multiple choice. But as you probably saw in the email that I sent and the notice, in these really, really rare times, there is apparently no more multiple choice. It looks like the AP exam is going to be 45 minutes online, just free response, most likely 3 free response questions. More on that later. Let's not worry about that now. Let's try to get through the remaining 6 lessons that we have to get through. D. On D, if I'm following the same logic here, I've got a lot more going on in this problem. It is kind of a complicated problem, to be honest with you. There's more than one way to do this, but I'm going to attack it just in straight up form. The way it's presented is the way I'm going after it. So it is shown as a general logarithm, and our formula says we go 1 over the input, 1 over technically square root of x over x plus 5. Oops, I'm missing something. 1 over the input times natural log of the base, and then times the derivative of that input, square root of x over x plus 5. And that is not an easy derivative, unfortunately. It's going to be a quotient rule problem. So let's focus our attention on this input first. First note that since this is technically ln of 3 over 1, it would be up here with the square root x. It'd be in the numerator with that square root of x. And since it's 1 over that, then technically the x plus 5 goes up top. We take the reciprocal of that denominator, and the x plus 5 is up top, and we're left with ln of 3 in the bottom. So it's going to look like this. X plus 5 over square root of x times ln of 3. That's how this expression will simplify. All right, then we've got the derivative of this square root of x over x plus 5. That's a quotient rule problem. That's the bottom function times the derivative of the top. The derivative of the top is 1/2 x to the negative 1/2 minus the top function, which is, I'm going to go ahead with square root of x here, times the derivative of the bottom. Derivative of x plus 5 is 1, and then it's all over x plus 5 quantity squared. All right. Now note, this is all multiplied by this previous expression over here, the x plus 5 over square root of x times ln 3. So the only thing I would say that I might do a little bit further beyond this is recognize that I have one expression of x plus 5 there and two expressions of x plus 5 here. And so therefore, I could cross one of these out and all of that out. And it leaves me a factor of 1 on the numerator there. Otherwise, maybe not a whole lot I can do to simplify. You probably go one more step and multiply some stuff out, or just leave it alone. I'm not going to go into the details of simplifying that. All right, let's move on to the next one. If I can, there we go. I threw one more example on here from a different text, so let's try it out. 1 over the input times natural log of the base. The input here is 2 plus sine x. Natural log of the base is natural log 10. And then we multiply by the derivative of the inputs, and that is basically derivative of 2 is 0, derivative of sine is cosine, so cosine x. So we can simplify that, put the cosine in the top, cosine x over, you can multiply by the ln if you feel so inclined, but I'd probably just leave it, to be honest with you. 2 plus sine x times ln of 10. Nothing else we can do. Very simple question. Remember, this was the derivative of the 2 plus sine x. That's what happened there. All right. That is the end of that page. Let's move on to the next one. All right, this is a quick review of exponential graphs. I'm not going to spend a whole lot of time on this. Just going to roll right through with a couple of fine details on exponential graphs. First and foremost, exponential graphs, grow exponentially. You've probably seen plenty of this when talking about the COVID-19 stuff and the growth of infection numbers and so on right now. But right now, what I need you to remember is that the natural and general exponential functions will all grow in a similar fashion. I think it's probably best to discuss in terms of the graph below here that has all kinds of examples. So if the base is a number greater than 1, the base is greater than 1, let me use the pointer here. The base is greater than 1, like this says, then you've got a graph that is increasing curve. It's going to approach infinity as x gets bigger and bigger and bigger. It's going to approach 0 as x gets smaller and smaller and smaller. So as we go to the left, we get to 0. As we go to the right, we get bigger. If that number is between 0 and 1, if the base of the exponential function is a fraction, a proper fraction, like 1/2 to the x or 1/4 to the x here, then it's a decreasing curve and the values are getting smaller. All right, that's one of the key characteristics and features that we need to keep in mind. One of the questions they love to talk about on AP exam is solutions when comparing exponential functions with others. And the key thing to remember is that exponential functions will always grow faster than any other kind of function. And so if you are looking at how many times does something like 2 to the x intersect with x squared, well, it's going to happen at least, well, in this case, exactly 3 times, 1, 2, and 3. Because even though it looks like on the right here between 2 and 4, it looks like 2 to the x is growing faster sorry, x squared is growing faster. 2 to the x will eventually surpass it. It's going to grow much quicker. The red curve increases faster than the blue curve. And so it intersects again over here. All right? And they got it zoomed in a little bit there. I'm sorry, zoomed out. Same picture zoomed out in figure 5. So we don't need to discuss that really. All right, let's move on. Occasionally, an integrand involves an exponential. An integrand involves an exponential function to a base other than e. When this occurs, there are two options. You can convert to base e, which is not an option that we generally take all the time, using the formula that we discussed right at the beginning of the lesson, where you can rewrite any general exponential as an exponential base e. Or you can integrate directly using some integration formula. That's the path that we generally take, is path number 2. All right, so the formula you want to learn is the one shown here. Integral of a to the x is 1 over ln of a times a to the x. Remember, the integral of e to the x is e to the x plus c. Well, it's technically e to the x divided by ln of e, but ln of e is 1. Well, now we're saying that it's the same formula whether you have e to the x or you have a to the x. Any base, not just natural base e. You divide, you take the general exponential, and you divide by its by natural log of its base. All right? Problem is, your exponent won't always be x, and so that's where u substitutions come in play. Let's play with it. Example 4 here is just base x, or exponent x, so that's really easy. So this is, again, if we follow the formula directly, it is 2 to the x, the original exponential, but because it's not base e, it's base 2, we're going to divide by ln of 2 plus c. All right, 48, if I can move over. There we go. This time, the exponent is not just base x, or I'm sorry, it's not just x, it is x squared. So we're going to do u substitution, let u equal x squared. Du is then 2x dx, which means we've got this extra factor of 2 we have to handle. So we're going to rewrite this integral 1/2 the integral of 2 to the u du. And then we follow the formula from directly above. We've got an extra factor of 1/2, so I'm going to write that out there. But then it is 2 to the u over ln of 2 plus c. And then we can put our x squared back in place. We've got 1 over 2 times 2 to the x squared over ln of 2 plus c. If you want, you can put that 2 down there in front of the ln of 2. That's fine. But this is good enough also. All right, let's keep rolling. All right, this is a neat little trick here. When the power rule that we learned way back when was introduced in chapter 2, the exponent n was required to be a rational number, meaning not like pi or e. The exponent had to be a rational number. Now the rule is extended to cover any real number. Any real number, doesn't matter. And there's a simple little proof here. If we use logarithmic differentiation, which you probably have forgotten by this point, so quick review of logarithmic differentiation. You begin by taking the natural log of both sides of your equation. We use this, by the way, on really complicated functions. Excuse me. Functions where the stuff we're dealing with on this right side of the equation is particularly ugly and we just don't want to have to differentiate when it's in that form. So we take the natural log, we split it up into smaller, better looking stuff. So take the natural log of both sides and you get the power rule tells us we can move the n out in front as long as the input is not zero and not negative. Of course, that's why they put the absolute value in there. Then you differentiate, and to differentiate the left side, it's y prime over y, or you could say 1 over y times y prime, which is equal to y prime over y. And then the derivative of the right side is 1 over x times the n that's already sitting there, so n over x. Then you multiply by that y and pull it back over. That's what they've done here, right? I should say if you're multiplying by it, it ends up looking like that. And put the y, which was x to the n, back in place, and you're left with n times x to the n over x. Well, if you divide x to the n by x, or x to the 1, is equal to x to the n minus 1. So no matter what that power is, the derivative of of x to the n is n times x minus 1. Is n times x to the n minus 1. It is their power times x to the 1 less power. Multiply by the power and then subtract 1 from the power. All we just did in this proof here was formally prove the power rule for differentiation that we learned way back in chapter 2. Probably didn't need to do all that, but there it is. Moving on here. So the power rule is an expression now that we can use for any power, real, rational or irrational. And there they are, shown once again. Not that we didn't know them already. Let's move on. You should distinguish carefully here between the power rule. I really want to stress this box here. Distinguish carefully between the power rule. I have different light stuff I can use here, like a lightsaber. Anyway, distinguish carefully between the power rule, which says take the derivative of x to the n, multiply by the power, decrease by the power by 1, where the base is a variable and the exponent is a constant, and the rule for differentiating exponential functions, where the base is a constant and the variable is the exponent. The base is a constant and the variable is an exponent. Those are very different rules. So please be wary of how you do this. Pay attention and make sure we're doing it according to the rules that we have established. So here they are. The derivative of a constant raised to a constant is just 0 because that's a constant. Derivative of a function raised to a constant is basically a chain rule problem. You multiply by the constant, you decrease the constant by 1. Again, multiply by the constant, multiply by the exponent, decrease the exponent by 1, leave the base alone, and then multiply by the exponent of the base. The exponential function in step 3, you multiply by, or you leave the exponential, you rewrite it, then you multiply by natural log of the base, then you multiply by the derivative of the exponential, and then finally, if both, number 4 is the one that's new to us, if both of them are exponential, are functions, if both the base and the exponent are functions of x, this is where we'll want to use the logarithmic differentiation that we just talked about. So let's play around with that in just a second as we get through these next group of problems. All right, so here in number 5, we've got the constant rule shown. We've got the constant rule says e to the e. This is basically a. These are just mimicking 1 through 4 here. So e to the e, constant raised to a constant. The derivative of a constant is 0. The second one, derivative of the x is e to the x. The third one, you multiply by the power. Since the base is x and the exponent is a constant, multiply by the power, decrease the power by 1. And then the last one you would have to use, it doesn't show you how to do it, but we're going to do it in a similar problem next, but you would have to use logarithmic differentiation to solve that. All right? I could do it, but for the sake of time, this video is already getting long. Let's move on. Number 4, differentiate. Logarithmic differentiation, because the base is a function of x and the exponent is a function of x. So I'm going to say this is f of x raised to the g of x. All right? So if I take the natural log of both sides, then I've got natural log of y equals natural log of x to the square root x. And the power rule for logarithms says I can pull that that square root of x out in front. Now I've got natural log of y equals square root of x times ln of x. All right, then I differentiate both sides. I can get y prime over y equals, on the right side I'm going to have to use the product rule. So this becomes square root of x times 1 over x. That's the derivative of ln of x. Derivative of ln of x is 1 over x. All right, and then I've got plus natural log of x times the derivative of my square root x is 1/2 x to the negative 1/2. All right. Oops. The derivative of square root of x here. So this is my first function times derivative of the second plus second function times derivative of the first. All right. So we could clean that up just a little bit before I multiply by y. Oops. So I still have y prime over y is equal to, when I multiply square root of x times x, that really just becomes 1 over square root of x. The algebra there. And then here I could write this as natural log of x over 2 square root of x. All right. And if I was really feeling like I had to simplify that more, I could multiply the first fraction by 2 over 2 to get a common denominator here. And put those together. And so now I have y prime is equal to 2 plus ln, whoops, I forgot the x up there. 2 plus ln of x over 2 ln of x. And then that is all multiplied by my original y, which was technically x to the square root of x. So final answer, if you were writing it all out, 2 plus ln of x over 2 square root of x times x to the square root of x. Ooh, it's kind of a bear, but there it is. When you have a function of x raised to a function of x, then you must use logarithmic differentiation. Well, you don't have to. There's an alternative method there, but logarithmic differentiation is definitely going to be the choice that you're going to want. Don't forget how to do logarithmic differentiation. It's very important. And then one of the key things that students tend to forget is multiplying by that y. The other method shown here is to rewrite the function using base e. I'm not a big fan of that because it confuses students, so I'm just going to let you look at it on your own. In the meantime, I'm moving on. Actually, I believe this is probably a good place to stop for now. I will complete this lesson, 5.5, the last 2 pages, which are on applications, some pretty simple applications. I will complete those in the next video.